All right, guys, welcome to our lecture on Module 3, Discrete Probability Distributions. I've already uploaded a live video on the introduction to Discrete Probability Distribution and what they are and what we're going to do. So I'm just going to go over the whole thing through the PowerPoint as if it was being done in class. We've talked about discrete probability distributions and how they are the actual theoretical version of a changing model that's done usually in an experimental manner. I showed you guys the concept and the fact that once you experiment something or you simulate an experiment in probability and stats and then you do the counting, the outcomes don't necessarily match your theoretical expectation. And I showed you guys the coin toss, and I tossed it so many times, and I counted the heads and tails, and you see it's coming up with 51 tails and 49 heads. Well, that's not that bad, but we were still expecting 50-50 if this is a fair coin. Then I kept repeating the experiment. Here especially, I get 38 tails and 62 heads. And so that obviously goes against our expectation because we were expecting 50-50 because it's a fair die. So and a lot of different examples like that, and even the roll of a die, we're expecting all the outcomes to be the same. But when I'm rolling a die 4 different times and I'm rolling it the same number of times, you see that all my distributions, they're all different. And what is it we were expecting? We were expecting something that's completely uniform, because our understanding is when you roll a die, the chances of getting any of the faces is the same, and it's equally distributed, and it's 1 out of 6. So this is why I explained to you the difference between experimentational probability or theoretical probability, whereas in experimentation, when you conduct an experiment, you're never going to hit your actual theoretical expectation, and every time you do it, you get a different value. So therefore, the concept of a frequency table sometimes is not convenient to use. We want to use a table that doesn't change every time you repeat the experiment. So that's when I introduced you guys to a replacement table. You can call it a probability table, but a more sort of elaborate name for it is a probability distribution, and that is instead of using frequencies, we use probabilities. And if you do that, then it will never change, because the probability of rolling a 1 in a fair die roll experiment is always 1 out of 6, whether you do it now or 10 minutes from now. So therefore, ergo, the creation or the beginning of the use of the concept of a probability table instead of a frequency table. Now, our objective in this chapter is going to be to construct these probability distributions, which I'm going to present in this portion of our video. And the second part of this module will be focusing on calculating the mean, variance, and standard deviation of these probability distributions. And then the third video will focus on introducing you to formulas that will help you create these probability distributions so you can then use them to respond to different probability questions. So let's start constructing these probability distributions, but in order to do that, we need to learn some names and understand some notations and language. Now, when we have a probability distribution, we have 2 columns. The first column are the numerical value of all possible outcomes. I'll repeat that. Numerical value of all possible outcomes. So 1 is a numerical value of one of the outcomes when you roll a die. 2 is a numerical value of another one. So is 3, so is 4, so is 5, and so is 6. So these are all different values that could occur when this experiment is conducted. These are the values that go in the first column. And what they are called, well, they don't have a specific name, they're just values, but the entity that produces them is called a random variable. And that's what we labeled the column with, a random variable. So not to mistake in the random variable as these numbers, remember, 1, 2, 3, 4, 5, and 6, these are not random variables. These are values that the random variable has generated. So in this case, in this example, the random variable will be the dot that appears on a die when you roll it. So we call that the label of the first column, and then we list all the values it could be. Now the second column will be the probability column, where you write down the probability of each one of these outcomes. which in this case is 1/6 all the way through. And there is what a probability distribution looks like. And there's always a hint that you could use, or a self-check, that when you calculate all the probabilities in a probability distribution, they all have to add up to 1. So if they don't, that means you've made an error. And this will be used later on to compute one of the probabilities if it's missing. Now we'll talk about that when we get to it. All right, we talked about the random variable and the fact that it just assigns values to outcomes of experiments. Here I've given you some examples of random variables. So the random variable could be the number of left-handed students in a class. It could be the number of delayed flights, the number of defective CDs, the number of students that have iPhones, and so on and so forth. Here's an example. Say we're dealing with a stats class with 26 students, and we're defining a random variable to be, say, students with blue color eyes, or we could define it to be number of students that have iPhones, or we could define it to be a number of students that are left-handed. But either way, once a random variable is defined and you have 26 students in this class, well, then the values that random variable assigns will be 0 to 26. Because you could have 0 students that have blue color eyes, or you could have all 26 of them that have blue color eyes. Or you could have 0 of them that have an iPhone, or you could have all of them that have an iPhone. So the values that the random variable assigns in this experiment are 0 to 26. Okay, so let's look at this example now. Say a coin is tossed 3 times, and we want to let the random variable x represent the number of tails. And it says construct a probability distribution. Well, we know we have 2 columns for our probability distribution. And here it is. It would be a column of what's labeled as the random variable and a column of what's labeled as P, stands for probability. Well, now it says the random variable represents the number of tails, and we're tossing the coin 3 times. So we could, if you think about it, it would make sense that the values that are assigned to the outcomes will be 0 to 3, because you could toss a coin 3 times and you can get none of them to be a tail, 1 of them to be a tail, 2 of them to be tails, or all 3 of them to be tails. So it's not that difficult to imagine that the values that you assign to the outcomes in this scenario will be 0, 1, 2, and 3. Now, the issue becomes, okay, great, that's simple. So I assign 0, 1, 2, 3 to the outcomes. How am I going to find these probabilities? Well, not that difficult, just with few minor recalls. Let's first remember that a probability is always a fraction. I'm going to write here on the side, probability is always a fraction of dividing part by the total. So don't forget that. So keep that on a back burner. Now, so therefore, it is clear to me that every one of these probabilities is going to be some kind of a fraction. Is that okay? Well, I assume so. So we know that every one of these probabilities that I've written here, this one, this one, this one, and this one, is going to be a fraction. And I also know that the denominator of my fraction here, because I have 3 coin tosses, and you all remember that the way you find a total number of combinations of 3 different coins, each having 2 different choices, will be 8 outcomes. You could also see it if you look at it here. If you list the sample space using a tree diagram from module 2, you could also see that there are 8 outcomes. So it becomes pretty clear that my denominators here will all be 8. Because the experiment doesn't change from one outcome to the next. So all my denominators are 8. Now, the problem becomes at this point, how do I know what's going to go in the numerator? Well, at this point, guys, all we could do is to look at the sample space, which obviously means you need to construct it, which obviously means you need to use a tree diagram to construct it, unless you've memorized it. So we have to go to this sample space here and actually count how many outcomes have 0 tails in them, how many have 1 tail in them, 2, and 3. Well, let's do it, see what happens. If I go back to my sample space and start counting the outcomes that have 0 tails in them, because I'm trying to figure out the numerator for the probability of that outcome. But if I come here to my sample space and then count how many of these have 0 tails in it, I'll find out there's only 1 outcome that have no T in it. which means the numerator of my first fraction has to be a 1. All right, I'm good with that. Let's move on to the second one. Now, I'm trying to figure out what's going to be the numerator for that one. Well, that means I'm looking for outcomes with only one tail in it. Well, that's one of them. That's another one, and that's another one. So these are the 3 outcomes that have one tail in them. So that means the numerator of my second fraction will be 3. And then I count how many of them have 2 outcomes in it and cross them out so you don't mix them up. So let's look at how many of them with 2 outcomes, 1, 2, and 3. Okay, so the denominator of my the numerator of my third fraction will also be a 3. And then ultimately, how many of them have 3 tails in them? And that's that one, so that's just 1. And don't be surprised, there it is, guys. It's really not that difficult. So we could do the same thing for 4 coin tosses, 5 coin tosses. Now, of course, the sample space will be larger and it'll be more of a pain, but the concept, the structure will still be the same. You first figure out your outcomes. You write them, whether it's 0 to 3, 0 to 4, 0 to 5, 0 to 6, it doesn't matter. Then you realize that all the probabilities are going to be some kind of a fraction. Okay, and then you figure out the denominator of each of these, which is the same, which is just 2 to the power of n, which n is the number of coin tosses. Remember the cell phone memory thing, 8, 16, 32? And that will do it. And then you just do the sample space and count the outcomes. So there it is. All right, let's move on. Couple of things to know about discrete probability distributions and their properties that are quite important. We've talked about this one already. And that is, once you calculate all your probabilities, they always have to add up to 1. And this one's pretty important too, and we've known this from module 2, and that's the fact that a probability is always a value between 0 and 1. So don't forget that. These are very important, and they're going to come in handy down the road. Basically, you mentioned that the 0.57 is a good probability, but a negative 0.57 wouldn't make sense. Okay, moving on. Steps in constructing probability distributions. You don't need me to go through this. You guys could read this yourself. I want to focus more on showing you structure and problems. Construct a probability distribution for number of girls in a family with 3 children. Now, do you guys all realize how this is identical to the one I just did? See, the one I did was, let me go back. The one I did was constructing a probability distribution for tossing a coin 3 times. Tossing a coin 3 times, 3 children, since both have 2 outcomes based on our assumptions, then these 2 mathematically will be identical experiments. So whether I ask you to construct a probability distribution for tossing a coin 3 times, or I ask you to construct a probability distribution for the gender sequencing for a family with 3 children, it will be an identical mathematical probability distribution. So you could look over all of this, which was saying the same thing I've already told you. And if I actually go down to the probability distribution, you realize that, yep, it's the same exact probability distribution. It was 0 tails, 1 tail, 2 tail, 3 tails in that experiment. Here, it's number of girls. So 0 girls, 1 girl, 2 girls, 3 girls. It could be number of boys. It could have been 0 boys, 1 boy, 2 boys, or 3 boys. And again, you notice here, you write all the denominators, and then you just count the numerators, and you get the same identical probability distribution as you got for the experiment of tossing a coin 3 times. So I want all you guys to realize at this point that you have learned only one thing. You've learned how to construct a probability distribution for an experiment that has 2 outcomes. And we've looked at specifically to the coin toss 3 times, 2 outcomes, heads and tails. So you've learned how to construct a probability distribution for tossing a coin 3 times and assuming that you're interested in number of tails. Now, by learning that one experiment, now imagine you could construct a probability distribution for any experiment that's being conducted 3 times and there's only 2 outcomes, and gender sequencing is one of them. And you could do this for 3 rows, for 4, for 5, for 6. The only pain here will be constructing the sample space so you can count the number of outcomes. That's the only pain that there is. And if you recall, I've shown you how to construct that on Excel. I just wanted to show you that for a minute. And I have that as 3 children. You see how I've constructed the gender sequencing for 3 children. Remember, you do 2 to the power of 3, which is 8. You break 8 in half. You write 4 boys, 4 girls, and then you write 2 boys, 2 girls, and then 1 boy, 1 girl, and just copy that down all the way to the 8th position. And it gives you the gender sequencing for 3 children. Same thing for 4 children. 2 to the power of 4 is 16. So do 8 boys and 8 girls, and then 4 boys and 4 girls, and 2, and then 1, and then just alternate it until the end of 16. And that's how you produce the sample space for having 4 children or 4 coin tosses. In that case, it would have been heads and tails instead of boys and girls. And you could do this for 5, 6, 7, 8 using Excel, so you don't actually have to do it with a tree diagram. Going back to our discussion. So moving on. And oops, here it is. Obviously, it says gender sequencing 3, 4, and 5 children. And you could see how each one is done the same way I told you. And same here. You'll see this is 4 gender sequencing. So 2 to the power of 4 is 16. So you know that all denominators here are going to be 16. Here's 5 children. 2 to the power of 5 is 32. So you know all my denominators are going to be 32. And the way you figure out these numerators is to basically go to the outcomes. For example, for 4 children here, you have 0 boys, 1 boy, 2 boys, 3 boys, and 4 boys. And you can count these. You have 1 of those, 4 of those, 6 of those, 4 of those, 1 of those. You can count these in here. So how many of them have 0 boys in them? Only 1. Let me draw this. How many of these have 0 boys in them? Only 1. How many of them have 1 boy in them? And then you could just count, this is 1 of them, 2 of them, so that you can count. And this is how these numbers are being created: the 1, the 4, the 6, the 4, the 1. I know it's a long way to do it, but that's the fundamental way to do it. But then if for folks that are interested in interesting creations by mathematicians in the past, there is a back alley way to this. There's a back door to this so that you could avoid having to deal with, let me show it to you again, producing these and counting them. And that back alley is what Pascal created, known as Pascal triangle. So students that want to go through the back alley, a back door to approach this and not want to create these sample spaces and do a whole bunch of counting and spend hours and hours doing it, all you have to do is just remember how Pascal triangle is constructed. You write 1, 1, 1. That's how you start. You start with a 1. You add the top 2 numbers, and you end with a 1. Start with a 1. Add the top 2 numbers. Add the top 2 numbers, and end with a 1. Start with a 1. Add the top 2 numbers. Add the top 2 numbers. Add the top 2 numbers, and end with a 1. So that's how they create this table. And you notice, once you create that table, and it's not that difficult to do, now to figure out the numerator of these probability distributions, at least the probability part of it, which is the most difficult part, you don't have to worry about doing any counting or anything. You could just come here and read these sequences. Just so write it on your paper, because you can write it up to any value you want. When somebody says 3 children or 3 coin tosses, you just go to the row and it says 1, 3, 3, 1, and oh my God, it actually gives you the numbers. It's a miracle. Or you go to 4 children, you go to the 4th one there after that, and then you just see 1, 4, 6, 4, 1, and there are the numbers, 1, 4, 6, 4, 1. Oh my God. And then you go to 5 children. See, I haven't lost my sense of humor, guys. So you go to the 5 children experiment. The numbers are 1, 5, 10, 10, 5, 1, and there they are. So second floor people are not going to have a good time with this, but we don't mind. So that's how you construct these probability distributions. And I could have told you to do the same thing. Instead of for 3, 4 children, I could ask you to do it for 3 coin tosses, 4 coin tosses, 5 coin tosses. That would have been the same thing. So you learn one thing and you can answer so many different questions that comes to you that way. All right, so that's that. Let's see. Let's look at this one. It says construct the experiment of rolling 2 dice and let the random variable x represent the sum of the dots on the 2 dice. And it's just basically asking us to construct the probability distribution for that. All right, for the sum of the dots. Okay, well, as I told you, this thing is going to pop up again. So you have it here. Okay, now you want to construct the probability distribution here for this experiment. And I'm just going to use the corner of it right here. And I'm going to use a blue color outlay here. Now you want to talk about the sum of the dots. And that's your random variable. So you basically at this point have to figure out how many different sums do the dots produce here in terms of every outcome of this experiment. Well, look at the first outcome. You have a 1 and a 1. So what do you think that produces? You have a dot and a dot. That's 2. So the smallest number is 2. Then the next one is that they add to 3. So the next sum that these outcomes produce is 3. And if you notice, it just moves on that way to 6 and 6, which is 12. So the sum will go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so those are the outcomes. Now, again, think about probabilities. Probabilities are always fractions. And the denominator of that fraction, let me do that. The denominator of these fractions is always the total number of outcomes. And you have it right here in front of you. The total number of outcomes is 36. So I know that every one of my denominators here is going to be 36. Okay, now it says, well, how many of these outcomes add to 2? That's only one of them. How many of them add to 3? 2 of them. How many of them add to 4? This one, and this one, so 3 of them. How many of them add to 5? This one, 1, 2, 3, and 4. So 4 of them add to 5. How many of them add to 6? 1, 2, 3, 4, and 5. So 5 of them add to 6. How many of them add to 7? 1, 2, 3, 4, 5, and 6. 6 of them add to 7. How many of them add to 8? 1, 2, 3, 4, and 5. So 5 of them add to 8. And you notice how now it goes all the way from 1 to 6, and then it goes back down from 6 to 1. So I don't have to count anymore once I see the pattern. Now it'll just be 4, 3, 2, and 1. And you just constructed the probability distribution for a roll of 2 dice. And you notice what's the highest probability here. And this shows you how I did it. And I have it here. What's the highest probability? Interesting. It's 7. And if you recall, in the game of rolling 2 dice in Vegas, the game of craps, you usually bust on what number? Yeah, 7. And why would the casino pick that 7 to be the one the clients or the people, the tourists that play that game bust on? Is because it has the highest probability of occurrence. And if you notice, if you actually draw the probability distribution for this and actually graph it, you see that very nice normal distribution behavior for this experiment. So anyway, so this is the experiment of rolling 2 dice and assuming the random variable is the sum of the dots. Now let's look at this question here. It's asking us to construct a probability distribution for a $100 bet on a number in a game of roulette. All right, well, in order for us to do this, we obviously don't need to be an expert in playing this game. I'm only focusing on betting on a number. You could do a lot of different betting in this game, but we're not teaching you gambling. We're just using an example of this, so I'm only going to be assuming that my only way of betting would betting on numbers. And all you have to know at this point that in this game, there are 38 numbers to bet on. And the payoff is 36 times, which means you could bet on numbers between 1 to 38. Well, it's actually 1 to 37 and 0 and 00, basically 38 digits or numbers to bet on. And then for every dollar you bet, if you win 36 times that amount. So for a $100 bet in this example, if you win, you will win 3,600. And if you lose, you'll lose that $100 that you invested making the bet. So now let's see how we can construct this probability distribution. All right, well, let me look at this. I'm showing it to you in a more rigid view there, the numbers that you could bet on. And we have two columns here, guys. The first column, or the column, are my outcomes. So what I need to do is I need to assign numerical values to the outcomes. Well, two things that can happen. I could lose, I could win. If I lose, I'm going to lose the $100 I used to make the bet. Obviously, they're not going to give me my money back. Wishful thinking, so you just lose that $100. Now, if you win, remember the payoff is 36 times. Which means if you win and your bet's $100, you get $3,600 back. But remember, $100 of it was yours, so you get $3,500. So that's it. So if you lose the $100. If you win $3,500. And those are your outcomes, numerical values of your outcomes. And some of you said it can't be negative. Why are you putting negative there? Please don't make that mistake. Probabilities can't be negative, not the values under X. So the first column could be negative. Of course you can have a negative outcome. You're not going to assume that nothing is ever going to be negative, like a temperature or loss in anything. So therefore, the first column could be negative. Your second column can never be negative. Don't mix that up. All right, so I have my outcomes. Now let's move on to probabilities again. Now, again, when you go to a probability column, don't lose yourself. Don't freak out. Don't panic. Start with always one thing in mind. Probabilities always have to be fractions. So I write a fraction. Unless the problem tells me the probabilities. Well, in that case, I just copy it. I don't need to worry about anything. So, and that could happen. So I write two fraction lines, okay, and then the next thing I have to worry about is, okay, well, my denominator, which is the total number of outcomes. Well, we're betting on numbers. What's the total number of numbers I could bet on? Well, that's 38 in this game. And if I ask you a question, it will have to be the same here. I can't just expect you to know any game in the world of gambling, so don't panic. You only are responsible to know the games I specifically talk about on this PowerPoint. Fantastic. So my outcomes are 38 in total. Now, if I'm betting on one number, then if that number hits, I'm going to win. That means the $3,500 will come to me only if that one number is hit. But if the number I have put my bet on doesn't hit, well, then I lose the $100. Or how many numbers are those? Since I'm betting on 1 out of 38 numbers, then that means I'm not betting on the rest of the 37 of them. So you notice that now I could clearly see that the probability that I'll lose a $100 bet will be 37 out of 38, and the probability that I win 3,500 will be 1 out of 38. And there is my probability distribution. And I have it written much nicer on the next slide, as you could see. And you could see, obviously, the probability of losing a whole lot more than probability of winning. Let's move on to another example. This is constructing the probability distribution when a fair coin is tossed 5 times. I've already done this with you in detail. You guys could just follow through here. I didn't do it with the sample space. I did it from the back alley door, which is the Pascal triangle. And I've outlined how to do it here for you, so you could go over this example yourself. The next one is a life insurance one. Lee buys life insurance, pays $1,200 for a $1 million life insurance policy. The probability that she lives is 0.9993. That will be given to you. And we want to construct the probability distribution. And you see it here done. Because you have two things can happen. She will live or she dies. If she lives, she loses the premium she paid. If she's died, somebody gets $1 million. So, unfortunately, not good for her, but good for her loved ones. Which is in turn good for her from being a kind person, human point of view. Now, what's the probability that Lee will live? Which means she will lose the premium that she pays for. And when I say lose, I mean from a mathematical point of view. Well, that probability is 0.9993 right there. Well, how would I know what that probability is? Well, here is when remembering that the sum of the probabilities must always add up to 1 will help us. Well, because if I don't know this probability here, and I only know this one, well, it's very simple. All I have to do is do 1 minus 0.9993, and that will give me the probability of what it would be if 1 minus 0.9993, which is 0.0007. So you see, here's when I used this idea from previous slides to help me figure out the second probability. And there is the probability distribution for this experiment. Let's move on. Here's our last example. It's a lottery ticket example. So you buy a lottery ticket for $20, like you win $1,000, $500, $300, and $20, or you lose the initial investment. And here I've written the outcomes as 980, 480, 280, 0, and -20. Because if you win $1,000, but you paid $20 to buy the ticket, your net winning is $980. So therefore, I subtracted $20 from each outcome. And obviously, it's possible for you not to win anything, and that's just -$20. Don't forget about that. And notice that for a $1,000 win, they're giving you the probability 1 out of 3,000. So at this point, I don't have to worry about figuring the probability out. It's given to me, and that's what I was talking about in the previous example. Well, let's write them all up. If I win $1,000, which is 980, that will happen with this probability. So there it is. If I win that much with that probability, I win that much with that probability, I win 0 with this probability, and I lose $20. And this, I didn't know. But since I know all the other probabilities, again, I know the sum of the probabilities adds up to 1. So if I know all the previous ones, I could just add all these up together and then subtract it from 1 minus all that. And if you do that, you'll find the missing probability. And that's how you could actually get the entire probability distribution. And when you're all making these divisions, go ahead and only use 4 decimal places. And this brings us to the end of the lecture. Next time, we'll talk about calculating the expected value of a probability distribution, which is the mean. We'll talk about calculating the variance, which is sigma squared, and the standard deviation, which is sigma. See you guys next time.